So in this section, we're going to continue on Unit 8, so a long unit, about other types of reactions, and these are going to be non-redox, or sometimes we also call them ionic equations. So let's start by talking about what is an ionic compound. We talked about it in another unit. We know that sodium chloride, for example, salt, the positive ions of sodium are attracted to the negative chloride ions, and they form a compound, NaCl. Well, if we take some salt and we dissolve it in water, what's actually happening? The NaCl doesn't really change. It's still NaCl, but what happens is the water molecules get in between the ions and they separate from each other. So if you remember back, I think it was in Unit 6, that we talked about polar molecules. Water is a polar molecule, which means that one end of the water molecule is positive and one end is negative. And so you can see in this picture the little water molecules. The oxygen in the middle is a little bit negative and the hydrogens are a little bit positive. They're not fully negative and positive the way the sodium and chloride ions are, but they are partially positive. So what happens is that the positive ends of the water molecule are attracted to the negative chloride ion and sort of surround it. And then the opposite, the negative end of water, are attracted to the positive ions, the sodium ions in this case, and they surround it. So you can see on the right-hand side that water sort of forms these little cages around the positive and negative ion. The water molecules are strong enough to pull the ions, to get in between the ions and pull them apart from each other. And so in salt water, you have negative ions and positive ions that are sort of swimming around, protected by these little cages of water. And when that happens, we call it aqueous. It's dissolved in water. And so just as a side, if you have salt in water, you can actually conduct electricity because the ions, the negative charges and positive charges, can move around. So here's some more examples that you can see a picture that's very similar to the one we just saw. The NaCl is a crystal where the ions are held tight to each other, and then where they're hydrated within the Na plus and Cl within the water cages. So you can see up above some other examples of aqueous compounds that dissociate. Dissociate is the word where they break apart and are dissolved in water. Dissociation or hydration, just the water. NaCl breaks apart, like we just saw, into Na plus and Cl negative. Well, what about something like Na2S? Well, one thing you need to know is that the two Nas are not really stuck together because they're both positive. They're both attracted to the S negative too. When it dissociates, all three of those ions will separately break apart, and so that's why you see on the right that I put 2 Na plus, because both of those will break apart, and then S minus 2. So the 2 does not stay as a subscript, but in fact comes out in front because there are 2 Na plus ions that break apart from every S minus 2 ion. The same thing happens with Na3PO4. There are 3 Na plus ions and 1 phosphate ion. Again, go back and review some of your polyatomic ions. The PO4 does not break further down, but it is the phosphate ion, PO4 negative 3. So that stays as 1 ion. So altogether there are 4 ions, 3 Na plus and 1 PO4 negative. So depending on the salt, you'll get different number of ions breaking apart. This will be important in a future lesson, I think, Unit 10, and so you probably want to remember this in the future. I thought that maybe the video would play as I was narrating this, and I can play the video and you can hear the voice, but you probably want to try going to this website and watching the video. It's a really a good video that sort of shows the salt crystals breaking apart. But I'm not going to play it here because you won't be able to see it. All right, so there's actually different ways that we can represent ionic equations. A molecular equation is what we're used to seeing, where we just have the molecules written as whole pieces. Then we can actually represent an equation by breaking apart the molecules into ions, like we just saw on the previous slide. We can break up the Na from the Cl or the Na from the S2 and write them as separate ions. And then, as you'll see, we can actually write them as what's called a net ionic equation, because usually what happens, only a few of the ions will react with each other and the others just sort of hang out. So let's look at an example of a molecular equation. In the molecular equation, each compound is represented by its chemical formula, and usually you'll see the parentheses what phase it's in. Okay, so in this equation on this slide, you'll see NaCl, AQ. That means NaCl is dissolved in water. As we've just seen, what that literally means is that the Na ion is separated from the Cl ion. But in this case, we've written it together, and the AQ just indicates to you that they are separated and dissolved in water. Same thing with the AgNO3. The Ag plus is separated from the NO3 negative. It's aqueous, but we just keep it together as the molecular form in this case, but the AQ indicates that it's dissolved. Now, on the product side, we have NaNO3. You may recognize this as a double displacement. The Na goes with the NO3 and the Ag goes with the Cl, so we've swapped in two different things, so double displacement or double replacement. Anyway, the NaNO3, because the AQ is next to it, we also know it's dissolved in water, so it stays dissolved in water. But now you see the final product, AgCl, has an S next to it. This just means that it is solid. It's a precipitate reaction. A solid has formed and cannot stay dissolved anymore. So in that case, the Ag and the Cl are stuck together even when they're dissolved in water. So if we take that molecular equation and we write it in terms of its ionic form, or the total ionic equation, all we do is anything that has the AQ after it, we just go ahead and break it apart into the ions, like we saw a couple slides ago. So the NaCl, which is aqueous, will break apart into Na plus and Cl negative, so we just write them as separate ions. The AgNO3 also breaks up in terms of Ag plus and NO3 minus. On the product side, the same thing. The NaNO3 is aqueous, so we break that apart into Na plus and NO3 minus. But because the AgCl in solution does not dissolve, it's got a solid, it forms a precipitate, then we keep it stuck together because it's not dissolved. So this in blue is called the total ionic equation because it shows all of the dissolved compounds as their ionic form, in their ionic form. So this is a total ionic equation. What you might notice, though, is that a couple of things show up on both sides of the equation, like the Na and the NO3. So what we can do is we can cross them out, sort of like an algebraic equation. If they show up on the left and they show up on the right, they're really just hanging out. They're not doing anything. For this reason, we often call them spectator ions. They're just spectating. Is that a word? They're just observing the reaction. So you can see that the Na shows up on both sides of the equation, and the NO3, same thing. So we cross those out. And then what's left over? The Cl negative and the Ag plus on the left, and then on the right, the solid AgCl. So in red, down here on the bottom, that equation is called the net ionic equation because it's really the main equation. It really only indicates the actual reaction that's happening. So the Na and the NO3, again, are just spectators and hanging out, so we don't need to put them in the overall equation. So this is something that's a little bit hard, a little bit interesting, but I'd like you to try to practice doing some of these ionic equations. So I think on the next slide another example. All right, so take the following molecular equation and write it as a total ionic equation and then as a net ionic equation. There's a few things that I want to point out here. That last example was a pretty straightforward example because everything was a 1. If there's 2's involved or other numbers involved, we have to be a little bit careful. So let's go through this one carefully. All right, the BaCl2 is aqueous. And so as I said earlier, the Cl2s aren't necessarily stuck to each other. All 3 ions, the Ba2+ and the Cl negatives, the 2 of them are stuck together. So when they break apart into all 3 ions. So you can see below in the blue line that I've written the Ba2+ ion and then taken the 2 out from the subscript and put it out front as a coefficient. So there are 2 Cl negatives. Same thing with the Na2S. The Na2, there's 2 of them. They break apart into 2 separate ions. So we put 2 Na pluses and then the S minus 2. Now on the product side, notice that the BAS has a solid by it. So that means we keep it together. It stays a solid. It's a precipitate or a solid. You can go back to the very first slide, the very title slide had that yellow ugly solid forming. That's what happens if you put 2 solutions that are dissolved and then you mix them together, and if a solid forms, what happens is it just kind of congeals or forms that solid thing in it. So the BAS just stays as a solid. We keep it stuck together. And then the Na and the Cl, this time they're 1 and 1, but notice that there's a 2 in front of them. So when we balanced equations earlier, we knew that that 2 distributes for everything that comes after it. So in fact there are 2 Na plus ions and 2 Cl negative ions, so that 2 distributes. And just a little word I kind of noticed, if you have a plus sign between reactants or products, the order doesn't matter at all. So notice that I had the BAS first on the black line and then it's at the end on the second line. It doesn't really matter what order you put things in. You can mix them all up and it would be the same thing. As long as you have the correct things on the correct side of the arrow, you're fine. So the blue line tells you what is the ionic equation, the total ionic equation. It shows all the ions that are present and it shows the solids that are present. It shows everything as they are actually occurring in solution. Okay, so the net ionic form, as we said before, is where you can get rid of all the spectator ions, the things that aren't really taking part in the reaction, but they're actually just there to get the other parts there. So like the Cl negative is just there to bring the Ba, and the Na is just there to bring the S, because the real reaction happens between the Ba and the S. So if we cross off the Cl negative and the Na plus, you see that we have 2 of them on each side, and we cross them out, then all that goes over is the Ba2 plus S minus 2, and that gives us BAS solid. So that is the net ionic equation, the essential equation. All right. Okay, so let's do another example. Step by step. Again, whenever we see something that's got an AQ around it, that means that we can break it up into its ions. So 2NaOH we can break up into the Na plus ion and the OH negative ion, and the 2 will distribute. And so, okay, they'll break up into those 2 ions. The CaNO3 also breaks apart because of the AQ. So you might not remember what the charges of some of these ions are. You may want to go back into Unit 5 to review some of those things. Remember that the calcium is in the second column, and so it has a +2 ion. The NO3 is a polyatomic ion, so it's better to go remember your polyatomic ions, NO3 -1. You can figure them out if you knew that the calcium was +2, and the fact that there's 2 NO3s with it means that each NO3 has to be a -1, or if you knew the NO3 was a -1 and there's 2 of them, which makes it a -2, then the calcium has to be a +2. And so it's kind of have to go back, and that's the thing about chemistry, you have to remember things that you've learned all along, and you have to go back and review them if you don't remember them. But anyway, the calcium and the nitrate can break apart, as we see here. So the calcium 2+, and then remember the 2 comes out front because each NO3 breaks away from the calcium. On the right-hand side, again, the calcium hydroxide breaks apart because we see the AQ after it. So calcium 2+ plus 2 OH negative. And then the 2NaNO3 breaks apart. And remember again that the 2 distributes, so we have 2Na plus 2NO3 negative. Now, if we look at this one, you may notice that everything cancels. So here, the 2 NAs cancel on both sides, the OHs cancel on both sides, the calcium cancels on both sides, and the NO3 cancels on both sides. If that's the case, what that means is that there is no net ionic equation, and therefore actually there is no reaction. So if I were to pour together NaOH and CaNO3 together, nothing would happen. They would just kind of, everything would still hang out in solution, and we would get no precipitate. All right, one more example. Right, the complete ionic and net ionic equations for the following molecular equation. All right, so again, when we see the AQ, that means we can break it apart. And let me just point out here, I didn't say it earlier, but so solids stay together, but also liquids and gases. So in this case, the H2O liquid will stay as one compound, and the CO2 gas, they're molecular, they're not ionic, and so they will stay stuck together. So we only break apart the things that are AQ. All right, so if we break up the HO4, it breaks up into 2H plus SO4 negative 2. Now, the CaCO3 does not break apart because it's a solid, so we leave it as it is. The CaSO4 breaks apart. The Ca is a +2, and the SO4 is a -2. And then the H2O stays together, and the CO2 stays together. So now, if we inspected this again, is the complete ionic equation. This time, we see that only the SO4 -2 can cancel out. The H plus is not the same on both sides. It's a H plus on the left-hand side, it's a H2O on the right-hand side. The calcium cannot cancel out because it's a Ca +2 on the right-hand side, but it's a CaCO3 on the left. So the only things that can cancel are the SO4. So then if we rewrite the equation, we can see that this is the net ionic equation. 2H plus CaCO3 gives us Ca2 plus H2O plus CO2. So I hope that you can practice a few of these examples and go back and look at them and see if you can do this by yourself. All right, this is a little bit of a change of pace. Mass relationships, stoichiometry. We're actually not going to cover this to the extent of the slide. So as I go along, I'll tell you which slides you can ignore. But I do want you to get just sort of the general gist of mass relationships. So remember earlier I said that a balanced chemical equation means that mass is neither created nor destroyed. Well, it's sort of the same thing when we're talking about mass relationships. If you start with a certain weight of reactants, you have to have the same weight of products produced. They may be rearranged and in different orders, but you can't lose any or gain any along the way. So before we talk about stoichiometry or mass relationships, let me do an example from everyday life. All right, so if you want to make a s'more, well, let's just, in this case, I'm going to use my recipe, which says that I need 2 graham crackers, 1 marshmallow, and 3 squares of chocolate. If I add those together, I will make 1 s'more or s'more. So we can see that the ratio of graham crackers is 2 to 1 marshmallow to to 3 squares of chocolate, and together they make 1 s'more. So what if you wanted to make 3 s'mores? How many graham crackers would we need? Well, you probably realize that you would triple it. If you want to make 3 s'mores, you have to triple everything. So that would mean you need 6 graham crackers. How many marshmallows? You would need 3 marshmallows. How many squares of chocolate? 9 squares of chocolate, and you can make 3 s'mores. So, sort of the same idea in a chemical reaction. The ratios always stay the same in a chemical reaction. All right, so what is the ratio of graham crackers to squares of chocolate? Well, it's 2 to 3. Does this ratio change if you make 3 s'mores? No, it's still 2 to 3. It happens to be 6 to 9, but it's still the 2 to 3 ratio. So these ratios are part of a balanced equation. They never change. And actually, we can convert from one to another. If you remember conversion factors, we can actually figure out how many of one thing we need by using a conversion factor using this balanced equation. So let's look at what we did. So let's say we have 8 squares of chocolate and we want to know how many s'mores can we make. Well, from the previous slide, we saw that we need 3 squares of chocolate for every s'more. So if I make my conversion factor, 3 squares of chocolate is equivalent to 1 s'more, and then I put my conversion factor as a fraction. Again, I put my squares of chocolate on the denominator because that unit will cancel, and I put s'mores on the top because that's what I want to know. So I start with 8 squares of chocolate, divide by 3 squares of chocolate, multiply by 1 s'more, and I get 2.67 s'mores, or 2 2/3 s'mores. So you could start with any number, use a conversion factor, and figure out how much you need. On the previous slide, we said, what if I want to make 3 s'mores? How many graham crackers do I need? Well, that's another conversion factor. If I want 3 s'mores, and I know that I have 1 s'more for every 2 graham crackers, then I have to multiply by 3. 3 times 2 is 6. That's what we do. How many graham crackers would we need if we have 8 squares of chocolate? Well, we know that the conversion between squares of chocolate and graham crackers is 2 to 3. We need 2 graham crackers for every 3 squares of chocolate. So if we have 8 squares of chocolate, we multiply by 2 graham crackers, divide by 3 squares of chocolate. Again, the squares of chocolate cancel out, and we get 5.33 or 5.34, approximately 5 1/3 graham crackers. So mass relationships we can convert from one to the other by using conversion factors. With a chemical reaction. So if we have this balanced chemical reaction, what does a balanced chemical reaction mean? Well, literally it means that if I have 2 molecules of H2S and I react them with 3 molecules of O2, I will produce 2 molecules of SO2 and 2 molecules of H2O. That's literally what this means. But we can put the mole concept to this. We can actually put a dozen. We could say if I have 2 dozen H2S, I can react it with 3 dozen O2 to give us 2 dozen SO2 and 2 dozen H2O. Or remember what a mole is. A mole is just a certain number of atoms. So we can say that 2 moles of H2S react with 3 moles of O2 to give us 2 moles of SO2 and 2 moles of H2O. So that is what a balanced chemical equation means. Now, we cannot say 2 grams of H2S plus 3 grams of O2 give us 2 grams of SO2 and 2 grams of H2O. We cannot do that because each of the compounds have different weights. And so the only way that we can compare weights in a balanced chemical equation is to actually figure out the molecular mass. So if you see that bottom line below, I took the molecular weight of H2S would be 34.1. Multiply that by 2 because I have 2 of them, and then 3 oxygens each weigh 90 they each weigh 32, so 32 times 3 is 96. Now, 2 SO2s weigh 128.2 grams, and 2 H2Os weigh 36 grams. Now, if you add everything on the left and everything on the right, find that, let me do this real quick, 68.2, you'll get 164.2 grams on the left, and you'll also get 164.2 grams on the right. And so we're not destroying anything, but again, as I said before, we're rearranging. And so just what I want you to remember is that you can compare a balanced equation using molecules, you can compare them using moles, but you cannot compare them with the balanced equation using grams. You have to figure out the molecular weight in order to compare grams of different compounds. Earlier we talked about s'mores, converting s'mores. So we can do the same thing here. So let's go through this example. If I have zinc reacting with hydrochloric acid, 2 hydrochloric acid, give us zinc chloride plus H2. Well, what is this relationship? Well, one zinc molecule reacts with 2 hydrochloric acid molecules to give us 1 zinc chloride molecule and 1 hydrogen molecule. We can also say that 1 mole of zinc reacts with 2 moles of HCl to give us 1 mole of ZnCl2 and 1 mole of H2. So what's the ratio of HCl to C2? HCl to H2? 2 to 1. We need 2 HCl's for every 1 zinc. So we can make any conversion factor like you see there. 1 zinc equals 2 hydrochloric acids. 2 hydrochloric acid equals 1 H2. 1 zinc equals 1 zinc chloride. 2 HCl's equals 1 zinc chloride. Any two of those can equal each other. Of course, they're not equal to each other, but they're equivalent to each other, so we can convert from one to another by using those. So if I had 0.36 moles of zinc, how many moles of HCl do I need? Well, because I need 2 moles of HCl for every mole of zinc, I need twice as many moles of HCl. So I just take what I know, 0.36 moles of zinc, multiply by a conversion factor, and notice that I have moles of zinc on the denominator, moles of HCl on the numerator, because that's what I'm looking for. The moles of zinc cancel, and my answer, 0.72 moles of HCl. In the second example, how many moles of CO2 will be produced if 0.56 moles of zinc oxide reacts? Well, in this case, we start with 0.56 moles of zinc oxide, and we know that we will produce 1 mole of CO2 for every 2 moles of zinc oxide. So in fact, we make half as much CO2 because of the 1-to-2 ratio. Now, why is this important? Well, if you were working in an industry and you wanted to know how much of something you need, this is the process you go through. So let me give you an example. Well, actually, we're going to skip this slide. But let's just look at the reaction. Li3N plus H2O, 3H2O gives us NH3 plus 3 LiOH. Well, NH3 is ammonia. So let's say we wanted to make this, we wanted to have this reaction, we wanted to produce ammonia, and we needed it for something that we were working on, and we needed a particular amount of NH3. We needed to know how much NH3 we needed. Well, we would want to know how much water we have to start with, or how much Li3N we have to start with to make the amount that we want. So again, we're not going to get detailed into this, but this is the reason why we need to know these mass relationships. If I was, take an example of an airbag, there's a reaction that takes place where one chemical reacts with another chemical to produce nitrogen gas, and that's what blows up an airbag. So if we know the particular amount of nitrogen that we need to create to fill up the airbag, we can then calculate how much of the chemical we need to start with to put in the airbag. And this is very important because what if we put too much? If we put too much, the airbag might overinflate and burst. What if we don't put enough in? the airbag might underinflate. And so mass relationships are important for that reason. But again, we're just going to do mole to mole ratios, and we're not going to do gram to mole ratios. So you can ignore this, and you can actually ignore slide 59, slide C, and slide 61. So we're not going to do we're not going to do molecular weight calculations. All right. One more topic in this presentation is energy in reactions, and we've talked about this before, and you know that oftentimes there's energy involved in a reaction. Energy doesn't have to necessarily be heat energy, although that's often the case. You know, when we burn our methane, our natural gas, or we burn our gasoline, a lot of times heat is a product. The reaction will warm up. Some reactions actually absorb heat and cool down. So there's often heat energy involved with the reaction. There's also other kinds of energy, like electrical energy. So if we have like a battery doesn't really, well, it does kind of get warm, but that's a sort of a side effect. The electrical energy is what we're using. There's also nuclear energy. There's light energy. You know, a lot of times a flame will give off light, so that's not necessarily heat and light. So there's different types of energy. Mostly, though, we're going to talk about heat energy for right now. All right, so if a chemical reaction releases heat, so if it's a product, we call that an exothermic reaction. Exo meaning out, thermic heat. So what are some examples of exothermic reactions? Well, if you burn a log in the fireplace, or if you start your grill, so we're burning propane in a grill, that's combustion, that will give off heat. If you dissolve an acid in water, usually what happens is it gets hot. The dissociation of the acid will release heat. Other chemicals, if you mix certain chemicals, they'll get hot. If you mix an acid and a base together, they'll get warm. Okay, some chemical reactions will absorb heat or require heat to make them go. These are called endothermic. So of course, endo means in, and thermic means heat. So putting heat into the reaction. Some examples of endothermic reactions: melting of ice. You have to put heat into the ice in order for it to melt. So the heat is absorbed from the air. Or a chemical cold pack. What happens usually is there's a chemical, ammonium nitrate, that's stored in a container, and then there's water also in there. When you crack it open, the two mix, and when they mix, they actually absorb heat from the surroundings, and so it gets colder because they take the heat in. So that's an endothermic reaction. I just wanted to let you know different ways that you can represent heats of reaction in a chemical equation. And so in exothermic, since heat is produced, we can often write, like you see on the first line, this is the reaction of propane plus oxygen to give us carbon dioxide and water, and then we wrote plus heat, so heat is a product. So you can just use the word heat, as we see here, or if you see in the second line, the 2043 kilojoules. Kilojoules is a type of unit for heat energy. And so you could actually write the reaction and then just put the amount of heat that's being produced as a product. So the first two are written with the heat part of the reaction. On the third line, you see the reaction, and then you see further to the right, you see something delta H equals negative 2043 kilojoules. So if you see a delta H and you see a negative sign, negative means heat is being released, exothermic. Endothermic reactions, and this reaction is actually ice melting, so H2O solid going to H2O liquid. So we can either, like before, we can either write the word heat. Heat is a reactant in this case. You have to put it in. Or you can figure out how much heat you need, and you can write that in. Not that you can do that, but if someone else putting them in a reaction can put the actual number. And so if you see a number, you realize that's how much energy you need to put in. It's endothermic if you see it as a reactant on the left-hand side of the arrow. If you don't see the heat listed in the actual reaction, like the third example, but you see a delta H, if it's a positive delta H, that means endothermic. So any of these ways are ways to write heat in as a product, exothermic, or as a reactant, endothermic. So that's enough for this segment of Unit 8, and we've got one more to go.